using a zero-order integrated rate law to find concentration change. So we're going to use the integrated rate law for a zero-order reaction, which is the concentration at time t is minus the rate constant times whatever the time is, plus the concentration of our reactant at t equals 0, aka the initial concentration. So in order to be consistent with my units, my rate constant is in molarity per second, so I am going to go ahead and work out that initial concentration and concentration at time t, because we're actually solving for the amount of time that has elapsed in this particular case. So concentration is moles per litre, right? So number of moles of solute initially is 400 millimoles in a 250 milliliter flask. So that is millimoles per milliliter. The eagle-eyed of you have probably already spotted that the milli is going to cancel out, but I'm going to be thorough and consistent because that's kind of my job, right? So 1 milliliter is the same as 10 to the minus 3 liters. So that takes care of that first conversion. So right now we're in millimoles per litre, and then I've got to convert millimoles into moles. So 1 millimole is 10 to the minus 3 moles. So as you can see, mathematically, that is cancelling out, but it is important to do it properly because we are actually cancelling those units, as you do, right? So millimoles is gone, milliliters is gone. We have moles per liter, which is molarity, and that comes out as 1.6 molarity. Now, assuming the flask, stays the same size, and the amount of moles has halved, right? So you can probably already do in your head that we're expecting our final concentration to be half of the 1.6, but we're going to work it out properly just to make sure. So it should be about 0.8, right? So now we only have 200 millimoles remaining. Volume is unchanged at 250 milliliters. Oh, I should have done a copy paste. That would have been much easier, wouldn't it? So 10 to the minus 3 liters is 1 milliliter, and then we'll do the same for the millimoles. 1 millimole. It's 10 to the minus 3 moles. Lovely jubbly. Let's do some lineides. There we go. Right, millimole, sayonara, milliliter, adieu, and we should end up with that equaling 0.8 molarity. So we've got our A0, we've got our AT, and our rate constant K is provided to us in the question, so we're going to rearrange and make T the subject of the equation. Be careful with minus signs, etc. So final concentration of A minus the initial concentration of A, whatever it is, over minus K. Don't forget the minus K. This is important because if you think about it, during the course of a reaction, the concentration will be decreasing. Yes, if a reactant's being used up. Therefore, the number, whatever you stick in for AT, is always going to be smaller than the number for the initial concentration, A0. So we're going to get a negative number on the numerator. So keeping the minus with the K in the denominator is important because we can't have minus time, right? Okay, so let's substitute. A at time t is 0.8 molarity minus initial concentration 1.6 molarity divided by minus K, which is given to us in the question as 0.0032 molarity per second. So if I stick that into my calculator, I'm going to get units. The molarity is going to cancel out, okay, with 1 over seconds. So if you inverse and inverse, you get the thing, right? So I know I'm going to get units of seconds, and I get 250 seconds. I'm asked for 2 sig figs, so I suppose I should write 2.5 times 10 to the power of 2 seconds to get that to 2 sig figs. All right, so whichever thing you're asked to find in the zero order rate equation, you find that thing. You may need to rearrange and solve. Just be careful that there is a minus sign in front of that rate constant K, but we should always get a positive value if we're solving for a concentration or a time.